Welcome to session 4.0, Pumping Systems. This EMSI training section covers energy basics on centrifugal pumping. Your presenter is Rick Mitchell. This module will give you an understanding of energy use in pumping systems in the residential and commercial sectors. The transfer of fluids can be an integral part of operation for many industries. Pumps have applications well beyond the simple pool pumps that you might find in a residential situation. They are used in irrigation, air conditioning and refrigeration systems, chemical and sewage movement, flood control and marine services. This diversity in application means that pumps can vary in size and application and may even consist of multiple pumping arrangements. According to the Victorian Government's Resource Smart publications, pumps represent approximately 27% of the electricity used by motors in the manufacturing sector and 20 to 60% of the total electrical energy usage in many industrial, water, and wastewater treatment facilities. Generally, pumps can be classified into two categories: positive displacement and centrifugal, which within themselves have a number of subclassifications. Positive displacement pumps, or PD pumps, move fluids by pressurizing the liquid, essentially squeezing it through the pipework with each rotation of a piston or shaft. Centrifugal pumps employ a spinning impeller to kinetically draw or push fluids through a body. The kinetic energy of the fluid is used to create a pressure increase in the diffuser section of the pump. Centrifugal pumping. In industry, centrifugal pumps are significantly more common than positive displacement pumps due to their ability to handle larger flow rates. They are also common in residential applications because centrifugal pumping is far more space efficient and has low maintenance requirements, with a characteristically long operating life. Centrifugal pumps can also operate over a broad range of conditions and have a low risk of catastrophic damage due to improper valve positioning. These pumps also offer the best opportunities for energy savings. The pump characteristic curve at left is a graphical representation of the relationship between flow capacity and generated head or pressure. This gives a good indication of a pump's performance and energy efficiency, as an expression of fluid power to shaft power. Manufacturers generally provide a chart that indicates the range of flow rate and system head for a particular pump. They can be a good resource when selecting a pump. We will go into more detail on pumping curves shortly. What is important to know is that the efficiency of a centrifugal pump is directly related to the ability of that pump to perform at, or near to, its best efficiency point, or BEP. A pump's BEP is the point at which its operating efficiency is highest and where that pump operates most cost effectively in terms of both energy efficiency and maintenance. Characteristically, centrifugal pumping systems do not have a steady continuous flow which would allow the pump to operate at its BEP. For example, imagine a pool pump. Pool pumps are designed to operate at a capacity to match the few times a year that the pool water is turned over. This means that the pump is sized to operate at maximum capacity year-round, even though it requires significantly less power and flow capacity for a majority of its use. When faced with a pump in an audit situation, it is important to understand how to calculate the energy use represented by the system. Here we start again with the base calculation. Annual kilowatt hours is equal to the calculated power divided by the efficiency of the system multiplied by the time in hours for which the system is run per annum. As energy efficiency is essentially a product of reducing the total kilowatts of a system, it can be achieved through either reducing the hydraulic power, increasing the system efficiency, or decreasing the time of use. In this instance, power is the value of the hydraulic power, which is equal to the product of the flow capacity, density of the fluid being pumped, force of gravity, and total head. To convert the product into an appropriate unit of measure, being kilowatts, we divide by 3.6 times 10 to the power of 6. System efficiency is equal to the product of the required fluid flow rate, the static pumping head, and the specific gravity of the liquid being pumped, divided by 4,600 times the required electrical power input. First, let's look at reducing the hydraulic power of the system, which is equal to the product of the flow capacity, fluid density, gravity, and differential head. Now, when you're performing an on-site audit, it isn't necessary to calculate the hydraulic power, as the kilowatts will be recorded either on a data tag or in the unit's manual, or on the unit itself. The image above shows a typical pool pump data tag with both the kilowatts recorded and a simple equation to convert horsepower to kilowatts as a check. However, we'll now go into the power calculations in more depth to understand the variables which influence the kilowatt requirement of a pumping system. Taking the hydraulic power formula will remove the elements that we can't influence, which in this case are the force of gravity and the unit measure adjustment. The flow capacity or flow rate of a pump is a hydraulic power variable that plots a volume of fluid against the rate at which it is moving. It is measured in cubic meters per hour. Flow rate is often equated with delivery rate, and for this purpose it is generally the driving force behind pumping selection and design. That is to say that simply people do not buy or use a pump based on its power, they buy it because it can deliver a fluid at a required rate. In this way, the power of the pump is merely in service to the flow capacity. Flow rate, or capacity, is rarely calculated in assessments. Instead, if that information is not available in a manual or on a data tag, the rate is measured from a tap, hose, or similar. To do this, you can use specialized flow rate equipment or simply measure the time which it takes to fill a container of a particular volume. Because the flow rate is generally the factor which determines the required hydraulic power, it can rarely be reduced in existing systems. This is only achievable in instances where the system is oversized, and in this case, it's generally not financially justifiable to replace an entire pump. You can, however, design out variables which hinder the ability of a pump to deliver fluids efficiently. Some of these design solutions include designing out turns and bends in pipework, reducing the friction in the pipes, or increasing the pipe diameter. When we talk about a pump, we must be aware that it exists as part of a much larger system. This system includes the pump itself, pump drivers, controllers, piping, and valves. In addressing efficient flow capacity, we must address piping friction losses or the total friction head losses incurred as a fluid moves through a system, resulting from bends, valves, contractions and expansions, leaks, material friction, and outlet losses. Efficient piping design looks to minimize distance and head, minimize the use of bends, valves, contractions and expansions, size piping to the required flow rate, select the appropriate piping materials, and address damages in pipework including leaks and scaling. The density of the fluid being pumped also has a great impact on the energy needed to move it. Essentially, the higher the density, the more power required. Think of it like trying to move a volume of stones rather than a volume of water. This table, modified from engineeringtoolbox.com, shows the density of some common liquids. Pure water, which is used in many instances where the exact density is not known, is equal to 1,000 kilograms per cubic meter. One of the few practical ways to reduce the density of a material or fluid is to dilute it with a less dense fluid, essentially creating a slurry. Slurries, or diluted fluids, work to make pumping more efficient by reducing the density of materials and therefore the power required to pump them. This is a common practice in industries such as mining and agriculture. A slurry can be a mixture of virtually any liquid combined with some solid particles. Slurries are generally categorized into two main types, settling or non-settling. The combination of the type, size, shape and quantity of the particles together with the nature of the transporting liquid determine the exact characteristics and flow properties of the slurry. Non-settling slurries are achieved when particles are fine enough to form a homogeneous mixture that results in the fluid having increased viscosity. The scale of particles also reduces the likelihood of damage or wear on the system, leading to a longer operation lifespan and less friction losses. Settling slurries are those slurries that are not able to achieve a homogeneous state, referred to as heterogeneous, due to their size or other characteristics. These can be useful if the material in the fluid being pumped is to be separated once transported, but will increase the likelihood of damage or wear on the system. Head loss is a measure of loss in elevation, velocity head, friction, and pressure head. Head loss is divided into two main categories: major losses associated with energy loss per length of pipe, and minor losses associated with bends, fittings, valves, etc. A pump can only deliver a liquid to a maximum height because the weight of the liquid above the pump mechanism becomes greater than the forces which are attempting to turn the pump or move the piston or diaphragm. Differential head is most significantly influenced then through reducing the distance between the pump and the head, though usually this is not possible. This table summarizes the opportunities for decreasing the running power of a pumping system and can be a good reference when assessing or making recommendations to retrofit an on-site pumping system. Energy efficiency can also result from an increase in the efficiency of a system. In this instance, efficiency can be measured as the product of the required flow rate, static pumping head, and specific gravity of the fluid being pumped, divided by the electrical power input and a factor to scale the units of measure. So firstly, we'll remove everything that we can't affect.
Due to a recent addition, I, Matthew Barham, will be presenting this slide. Flow rate is equivalent to flow capacity, as covered previously. Rather than motor power, flow rate is generally the decisive factor in the sizing of a pump for installation. This is because pumps are generally installed to deliver product X by time Y. It simply isn't useful to have pumps that are oversized or undersized, though most err on the side of oversizing pumps for safety. Flow rate, because of a recent addition, I, Matthew Barham, will be presenting this slide. As covered previously, rather than motor power, flow rate is generally the decisive factor in sizing for pumps for installation. As covered previously, rather than motor power, flow rate is generally the decisive factor in the sizing of a pump for installation. This is because pumps are generally installed to deliver product X by time Y. It simply isn't useful to have a pump that is oversized or undersized, though most err on the side of oversizing pumps for safety.
In addition to the previous initiatives, variations in demand can also be addressed through the use of variable speed drives, multiple speed motors, multiple pump arrangement, which will be covered later, and maintenance and recalibration. It is uncommon to find a situation in which both flow capacity and demand on a pumping system is constant. What this means is that it is unlikely that such a pump would be able to run at or near to its BEP, increasing energy consumption and wear on the system. Variable speed drives or variable frequency drives are a system for controlling the rotational speed of an alternating current electric motor by controlling the frequency of the electrical power supplied to the motor. VSDs vary the pump's rotational speed, allowing it to change or adapt to the demand. This can be set either manually or automatically depending on the complexity and scale of the system, and of course the budget. By reducing the pump's rotational speed to match the demand of the system, less energy is required to run the pump. As you can see on the right, the more settings, depicted by the pump curves, the closer the pump is able to operate to its best efficiency point. However, in the instance that a pump naturally operates close to its BEP, little savings are actually achievable, as VSD pumps operate with less efficiency than traditional pumps and generally reduce the lifespan of the pump. Similar to variable speed drives, multiple speed motors can respond to varying load conditions by matching the energy imparted to the fluid to the system demands. Multiple speed motors employ a different set of windings for each motor speed, and allows the motor to work closer to its BEP. However, once again, the efficiency of these pumps is less than that of a single speed. Effective pump maintenance, coupled with monitoring, can significantly increase not only the operating efficiency of a pumping system, but the lifespan as well. Regular maintenance reduces the impact of damage to the system, such as wear from abrasive fluids, scaling of pipework, electrical failures or failures in the pump itself, and leaks in pipework or valves. To stay on top of maintenance, the system should be regularly monitored and reviewed, and equipment recalibrated where necessary. Static head is the head of water a pump must overcome before it will produce any flow. It is a result of the height difference between the suction water level and delivery water level. Simply, it is the maximum height or pressure it can deliver. Once installed, there is little room to reduce the static head of a pump. However, increasing pipe sizes, using appropriate materials, addressing demand, or even reducing the density of a fluid will affect the ability of a pump to move that fluid. Specific gravity is the density of a fluid in comparison to another fluid, generally pure water for liquids and air for gases. This table, modified from engineeringtoolbox.com, shows the specific gravity of some common liquids. Pure water, which is used in many instances where the exact density is not known, has a specific gravity of 1. Generally, the specific gravity of a fluid cannot be affected except where the fluid has been diluted to create a slurry or mixed fluid. The electrical input power of a pump is generally predetermined by all other efficiencies and power requirements. That is to say that the requirements and parameters of the pumping system are determined as a priority, and then a pump size is selected to deliver to that value. However, there are a number of different pumping configurations available to increase the efficiency with which a system will run, including selecting a pump that operates near its BEP, fitting a multiple speed pump or pump with multiple or lower speed arrangements, and trimming or changing the impeller. A pump which runs significantly higher or lower than its best efficiency point, right or left of the dotted line, respectively, will have a higher likelihood of excessive noise and vibration, reduced lifespan due to stress on the system, and increased power needs. A pump is usually considered over or undersized if it operates outside of 20% of its BEP. It is crucial, particularly if implementing a single-speed pumping solution, that the pump is sized to deliver at, or as near as possible to, the point of best efficiency, and that the BEP is representative of the maximum required pump use. The BEP is typically supplied by the manufacturer and can usually be found in the accompanying manual. Multiple pump arrangements. Because single-speed pumps are unable, in most cases, to operate efficiently where a large range of system requirements are present, and multiple or variable speed pumps are not able to achieve the required flow capacity, it may be necessary to employ multiple pumps. Multiple pumping arrangements are those systems which incorporate a number of smaller pumps in combination to deliver over large variations in flow rates. There are several advantages of using a series of smaller pumps over a larger pump outside of allowing the individual pumps to operate closer to their BEP. Significantly, the operating flexibility awarded by the arrangements is highly desirable in applications where the flow capacity varies frequently. It should be noted, though, that it is important for each pump to run above their minimum flow requirement to safeguard against wear or damage to the pump. An impeller is the rotating component of a centrifugal pump that accelerates the fluid inside the pump. It is comparable to the fan blades of an exhaust. For each pump, there are often a number of impeller sizes available, which have a dramatic effect on the energy imparted to the fluid. Increasing or decreasing the diameter of an impeller will increase or decrease both the flow rate and the measure of head achievable, respectively. Impeller trimming is a practical way of reducing flow capacity where a pump has been oversized. This table summarizes the opportunities for increasing the efficiency of a pumping system and can be a good reference when assessing or making recommendations to retrofit an on-site pumping system. Positive displacement pumping theory. Positive displacement pumping works by drawing a fixed volume of fluid into an expanding cavity and forcing it through a discharge cavity as it collapses. Because of this cycle, unlike centrifugal pumps, PD pumps are able to deliver a set flow capacity at a given speed, regardless of discharge pressure. Positive displacement pumps can be divided into two main classes: reciprocating pumps and rotary pumps. There are two main types of reciprocating pumps: plunger pumps and diaphragm pumps. Reciprocating pumps work by drawing a volume of fluid into a fixed cavity or pumping chamber through an inlet valve which is closed after the cavity is full. The fluid is then pressurized by reducing the size of the cavity using a piston or diaphragm and forced through an outlet valve. This is essentially how the engine in your car works. There are three main types of rotary pumps: gear pumps, vane pumps, and screw pumps. Rotary pumps work very similarly to reciprocating pumps in that they draw a volume of water into a fixed casing through an inlet. However, rather than displacing the fluid by use of a piston or diaphragm, they employ the principles of rotation. The vacuum created by the rotation of the pump captures and draws the liquid in, and the velocity added by the rotation propels the fluid forward. There are a number of instances in which positive displacement pumps should be used over centrifugal pumping. To make a good choice between these pump types, it is important to understand that these two types of pumps behave very differently. The following comparisons have been sourced from pumpschool.com, a valuable resource if you are planning to make recommendations on the sizing of pumps. Centrifugal pumps have varying flow rates depending on pressure or head, whereas PD pumps have more or less constant flow regardless of pressure. Changes in pressure have little effect on PD pumping, but have a dramatic effect on centrifugal pumping. Centrifugal pumps lose flow as the viscosity increases, however PD pumps' flow actually increases. This is because the high viscosity liquids fill the clearances of the pump. causing a higher volumetric efficiency. Because the centrifugal pump operates at motor speed, efficiency goes down as viscosity increases due to increased frictional losses within the pump. Efficiency often increases in a PD pump with increasing viscosity. Pumps often exist as a component part of a system and not the entire system. When used as a pool or pond pump or tank pump in a commercial process, the pump often works in conjunction with a filter and other various components. Filters work to remove impurities in water or fluids by means of fine physical barriers or chemical or biological processes. Smaller filters, like pool filters, use sand or cartridge filters, while larger commercial filtration may involve chemical or biological treatment. There are several processes involved in the filtration process, but the most common are turnovers and backwashing. Turnover is an important concept in pumping where filtration is concerned. It refers to the total time taken to run a full body of fluid through a filter. This is important for two reasons. Firstly, pumps that are required to perform turnovers are generally sized to operate at the maximum capacity required to achieve this. This is often significantly over the required capacity for regular operation. For example, the theoretical energy required to circulate domestic pool water is 50 watts. Commonly, pool pumps are 1000 watts. This is where variable speed devices can significantly decrease energy consumption by reducing the time for which pool pumps operate at maximum required capacity. Secondly, the turnover time can be used to determine kilowatt requirement to turn over the volume. To calculate the total power required to turn over a volume, power in kilowatts is equal to the product of the flow rate in cubic meters per hour and the static head divided by 367. Note that this only applies for pumping water. For example, a residential pool pump has a flow rate of 5,000 litres per hour and the pump is located half a metre above the height of the pool. In this instance, Q, or 5,000 litres per hour, is equal to 5 cubic metres per hour, and the static head is 0.5 metres. Here we can see that the pump requires 6.7 watts to turn over the pool at a rate of 5,000 litres per hour. Sand filtration is a much older technology than cartridge filtration. Sand filters work by passing water through a bed of finely granulated sand. As the water passes through, impurities are trapped or caught in the sand. The more sand, the more efficient the filtration. Sand filters are easily recognizable as they are large spherical shaped fiberglass globes with a valve and a bleed off at the top of a plastic window for view of the sand inside. As with any filter system, sand filters must be cleaned to remove the impurities trapped in the sand. This is done through a process called backwashing, in which water is run back through the filter and out through a secondary set of pipes, either to the garden or sewer. This process wastes a large amount of water, but is necessary to the efficient running of the filter. The more unclean a filter, the more pressure, and therefore power, is required to move fluid through the system. Backwashing should be done when the pressure gauge indicates a pressure rise of 8 to 10 pounds above the clean or startup pressure, or when flow rate is significantly reduced. Cartridge filters are a more recent technology than sand filters. They are recognizable as being much taller and thinner, with cylindrical housing that houses a series of fabric filters. Pool water flows from the outside of these tubes through the micro-sized pores which effectively carry out the same process as the sand in a sand filter, then is returned to the pool. Because of the increased surface area of smaller pores, many consider this to be a more efficient and preferable type of filtration. Comparing the two systems, it comes down to a trade-off between effort and savings. Cartridge filters do not need to be backwashed, meaning they don't waste anywhere near as much water cleaning the filters. Instead, the filter is pulled apart and the fabric of the filters is rinsed to remove impurities. This is a time-consuming process compared to backwashing a sand filter, but reduces the cost of refilling the pool. Generally, cartridge filters are more efficient than sand filters, though this is obviously dependent on size and quality. However, the cost of replacing the filters in a cartridge model can be as much as $200 per filter. In general, the efficiency of a cartridge filter negates whatever difficulty is incurred in cleaning or replacing the filters, and they are frequently preferred to sand filters. Chemical filtration is usually found in water purification processes in industrial applications, though it is sometimes found in specialist medium enterprises. There are a number of different methods to chemically treat water and fluids, including ion exchange, adsorption, chemical bonding, and molecular destruction. There are different media that you can use in the chemical filter, however, this form of water treatment is rare. In this instance, as with sand and cartridge filters, kilowatt hour use per annum can be calculated simply from kilowatt consumption, usually rated on the pump itself and time of use. More uncommon are biological treatment filters, such as constructed wetlands or photobioreactors, which use non- or low energy intensive processes to treat water naturally. Let's work through an example scenario. Question 1. Determine the total annual cost of running a centrifugal seawater pump with the characteristics shown in the table. Firstly, we'll calculate the power use of this system. Taking the information we know, begin calculating the hydraulic power. The total hydraulic power required to run the system to the required flow capacity is 6.86 kilowatts. Now we'll account for the efficiency and the time of use in order to calculate the true kilowatt hour usage of the pump per annum. We now know the hydraulic power is 6.86 kilowatts, the pump efficiency is 62%, and the time of use is 3,120 hours per year. The total true use of the pump each year is 34,521.3 kilowatt hours per annum. The cost of the system is then the total kilowatt hour use multiplied by the total cost per kilowatt hour, which we know is around 11 cents. So the cost of running the pump at the required flow rate would be $3,994.11 per annum. To continue with presentations, please select Energy Session 5.0, Thermal Performance and Climate Control from the navigation bar. To complete the assessment for this presentation, please select Tutorial 4.0, Pumping Systems.